let's look at the concepts of mass, weight, and apparent weight. So we have already defined what is weight. We have defined that as the magnitude is mg, and the negative sign represents the fact that weight is pointing down. Now, mass is the quantity of matter in an object, and it defines the concept of inertia. The more the mass of an object, the more the object has this ability of resisting its state of motion. So if a heavy object, we know from experience, is at rest, it's difficult to move it, and if it's moving, it is difficult to stop it. So we say that it has more mass or more inertia, that it has more a greater ability to retain its state of rest or motion. There's something called so there's something called apparent weight, right, that is different from weight. And the apparent weight is basically what we sense. So when you're standing on the floor, there are contact forces, right? The normal force that you feel gives you a sense of your weight, right? So that sensation is called apparent weight, and that sensation can change. So if you're in an elevator, your point of contact, right, experiences a change, right? So you feel that you're getting lighter or heavier based on your contact forces with the floor of the elevator, right? So that's where the concept of apparent weight comes in, right? So let's look at the concept of the situation where you are in an elevator, right? So when you're in an elevator, let's say that the elevator is moving up and speeding up. So this is, exactly, almost the same as the string example we did, where the string was moving, the mass attached to the spring was moving up and down, speeding up, moving up, speeding up, moving up, slowing down. So the few situations we looked at. So in this case, it's just that we have the normal force instead. So if let's say the elevator is moving up and speeding up, the acceleration is in the upward direction. So that means that the net force is in the upward direction. So this person is experiencing a normal force in the upward direction, and then the weight of the person is down, right? So that's the free body diagram. So if you write down the equation for this person is N minus W equals MA. So then the normal force is the apparent weight that the person is experiencing, and therefore the person experiences being heavier than usual. So that's what is the apparent weight. It's all related to contact forces. So that is why when astronauts are if you go on particular flights, they let you feel weightlessness, right? Obviously you're not massless, you're weightless, because you lose all contact with the surface, right? So that's free falling. So astronauts are basically continuously free falling objects, and they experience weightlessness, and that is what you experience when when you lose contact. Your weight starts decreasing. It's because that's what you're feeling is your apparent weight. And then, God forbid, if the cable breaks, then people lose contact with the surface at all. There's no contact at all. So the elevator becomes a free falling object, and you become weightless in the elevator. So let's look at this question. I already answered it, but let's check if you were listening carefully. So we have a 50 kilogram student, right? The mass of the elevator is given 1,000 kilogram, and the student is standing on a weighing scale. Now, the elevator cable breaks, right? After a few seconds, so the elevator starts free falling. What's going to be the reading on the scale? Pause the video, think about it. Okay, so the answer is 0, right? Because obviously the person loses contact with the surface, with the bathroom scale or the weighing scale, and therefore the person becomes weightless, and therefore the answer is going to be 0. Okay, let's answer on the question. In this case, the mass of an astronaut on the surface of Earth is m, what is her mass on the surface of the moon, and the value of G is given. Pause the video, think about the answer. Okay, I probably got you on this one. It's a trick question. The mass of the mass is independent of where the person is. Even when astronauts are in space, they're weightless, but they're not massless, right? The mass stays the same. It's the amount of matter in an object, quantity of matter in an object. So therefore the answer is M. Okay, so the weight depends on G, but not the mass. Mass is independent of that. Let's answer another question. So in this question we have a box is being pulled to the right at steady speed, right, by a rope that angles upward, and so this situation is shown over here. What is going to be true about the normal force in this question? So pause the video, think about it. You may want to draw the free body diagram in this case. That's going to help you get the answer. Okay, so the answer is C. Right? Now, as I said, I pointed this out, I think in one of the slides, that there's a misconception that normal force is always equal to mg, and that's not true, because whenever there is a component of the force that is not resolved, so tension is at an angle, so there's a component of tension that is affecting the value of the normal force. So you can see that the normal force, right, is up. There's a t sine theta over here, right? T sine theta over here, and then there is a t cosine theta over here. There are two components of the normal force, right? So if you write down the equation in the y direction, right? So obviously there is no motion in the y direction, so the net force is 0, which means that the t sine theta plus n is minus w equals 0, or this is just equal to mg, right? So all the forces in the y direction are equal to the upward forces are equal to the downward forces. So the normal force you can see is mg minus t sine theta, and so therefore n is less than mg. It's not mg. It's because of that component of t sine theta that is with the normal force that is decreasing the normal force. Okay, so let's stop over here for apparent weight, and on the next video I'll show you. I will describe what is friction and what are the types of frictional forces.